So now we can go over our alkyne nomenclature practice. And again, we're going to start off pretty easy. You can see in this first example, our longest chain goes right down the middle. And we know we're going to need to number this one from left to right. Why? Because just like with alkenes, same thing is true for alkynes. The functional group itself, the alkyne, gets priority over any substituent. And so if we number it this way, our alkyne starts at 2, whereas the other direction, it wouldn't start until the 5th carbon. So here we've got 7 carbons, which is heptane. Given that it's an alkyne, it'll become heptyne, and specifically 2-heptyne, or hep2-ine, because the alkyne starts on carbon 2. The only other piece we need in this case are these 2 methyl substituents. They're both on carbon 6, so we have 6,6-dimethyl hep2-ine. Our second example is also extremely straightforward. Molecules that are symmetric always make life easier because you can number it in either direction. It doesn't matter. So I'll do it this way, which is 6 carbons for hexane. There are 3 alkynes though. So just like with alkenes, if you're going to have multiple alkenes, you put a prefix in front of the ene. Same thing with alkynes. 3 alkynes is going to be tri. So 3 alkenes gave us triene. 3 alkynes give us triine. And we just need to list each of the numbers. And again, remember that when it comes to alkynes, E and Z doesn't apply. That's only with alkenes. So we don't have to worry about that for these examples. Now for number 3 here, we've got something a little bit more complicated, because we've put both an alkene and an alkyne into this molecule. So how do we do it? Well, everything's the same, just the parent name is going to change a little bit. Again, we number it to get the lowest possible number for our functional groups. If we ever have a tie, the alkene takes priority over the alkyne. But this is 6 carbons. There's an alkene on the first carbon and an alkyne on the third carbon. So we just put both of them into our parent name, hex1-ene 3-ine. This is a good example, though, of why we want to get used to putting those numbers internal to our name. Because if we just said 1,3-hexene-ine, then we don't know. We don't know if the ene applies to 1 or if the 3 applies to the alkene. There's no way to know. And so this is why we're going to put those numbers in the middle of the name as opposed to out front. Otherwise, in this molecule, we just have the 2 methyl substituents, so 2,5-dimethyl hex1-ene 3-ine. All right, number 4. We have our longest chain here. And I think we can see pretty clearly we're going to want to number it from the left side because that's where the alkyne begins. If we started here, we get our alkyne starting at 1, whereas if we went the other way, our alkyne wouldn't start till 6. So this is going to be hept1-ine, and we have 4 isopropyl, 3 methyl. Anything else? Don't forget your stereochemistry. At carbon 3, we have S and 4R. no matter how many functional groups we do in this class, don't forget the stereochemistry. That's one of the most common errors I see, especially as we get further along in this class. At some point we'll also add in nomenclature of alcohols, thiols, ethers, ketones, aldehydes, carboxylic acids. No matter how many of those functional groups you've learned or how many of them are in a compound, you still have to do the R&S when it applies. All right, this last one is looking for you to draw 6 possible compounds with the formula C4H6. And one way to think about this, if we have 4 carbons, and no double bonds, no triple bonds, no rings, the formula there is C4H10. Now, if we add in a ring, that takes away 2 hydrogens. So we're at C4H8. Same thing, if we put in a double bond, that also takes us to C4H8. If we put in a triple bond, that takes away 2 sets of hydrogens, so it takes us to C4H6. So the way we're going to get from C4H10 to C4H6 is we can do any of the following. 1 triple bond, 2 double bonds, 2 rings, or 1 double bond and 1 ring. Again, each time we add a double bond in, that takes 2 hydrogens away. Each time we add in a ring, that takes 2 hydrogens away. If we put in a triple bond, that takes 4 hydrogens away. And so there end up being 9 different molecules that you can draw that look with this formula. And as I bring over the answers, which went not at all where we wanted them on this page, but we'll move them down. That's what you'll see in each one of these examples, is that we've done exactly that. So you can see these first 2 compounds each have 1 alkyne in them. These next 2 compounds have 2 alkenes. We have a compound here that has 2 rings. And finally, we have 4 compounds that have 1 double bond, 1 alkene, as well as 1 ring.